G'day lads and ladies, and welcome to another episode of What's Up Mate podcast. A podcast for Australian electricians, refrigeration techs and air conditioning techs by an Aussie Sparky and Fridgie. So, what did we do last week? Last week we spoke about the rulebooks AS3000. Again, people call that the Bible for whatever reason. Obviously, I think it's because it's probably a large book that gives us most of the insights into our trade. So we spoke about Section 1 last week, and Section 2, it was a huge episode, I think like 74 minutes. It was something ridiculous, so I apologise for that. I'm going to go through section at a time now. So Section 1 is the scope, application and fundamental principles of the rulebook and what we need to do in order to keep people safe. And every section after that is how we go about doing it. So Section 2 was general arrangement and control and protection of your electrical installations. And this week we're going to move on to Section 3, which is selection and installation of wiring systems. And I guess as I go through this, I'll give you some examples of what we've done in the field where I can. So I've not actually scripted this at all. I'm just going to go through the rule book. So I've actually got AS3000 sitting in front of me as a PDF. So Section 3 in NZS 3000 2018 is starting on page 149. But before we get cracked into the subject matter, let's have a bit of a chat about what we got up to during the week. So Monday morning, as usual, we started off with a toolbox meeting. We do that every Monday. We'll have a team toolbox. For myself, this week we've done a lot of new home stuff. I've gone out and visited multiple sites. We've been awarded a couple of large projects too, which is nice. Our big VRF install out with the boys at MG Group in Salisbury. That's actually all the refrigerant pipework, drains, interconnecting cabling's all being completed. We've got that on pressure test. We're just waiting for the sparkies now to energise so we can then evacuate, add refrigerant charge. Let the crankcases on those compressors heat up, and then we can start commissioning. So yeah, that's going to be pretty exciting when we get that one up and running. One of our Sparkies is back on Monday. He's back from a 4-week trip to America, so pretty excited to have a chat to him and see what he got up to. But yeah, I've been to America once myself to play a bit of sport, and it's actually exactly like the movies. When you watch a movie that's based in America, when you go over there, it's actually pretty on the money. So, righto, let's move on. Let's get into Section 3, selection and installation of wiring systems. So, Section 3, the application of this section is, it specifies the minimum requirements for the selection and installation of wiring system that shall be achieved to satisfy Part 1 of the standard. So again, straight away, it's referring back to Part 1. So Part 1 is what we need to do. Parts 2 to 8 are going to be how we're going to go about doing that. So first it goes off, so 3.1.2, selection and installation. Wiring system shall be selected and installed to perform the following functions or have the following features. So we need to obviously protect against physical contact with live parts, but durable insulation materials or placing live parts out of reach. So out of reach, whether that's because we've got, transmission lines out in the street that are exposed, there's no insulation on them, you can't touch them normally unless they've fallen down in a storm. We've got, if we do have live parts in an installation that people can touch, only authorised people are supposed to touch them, so they're going to be behind locked enclosures. Or when we run cables, we've got sheathed cables. We're not running bare conductors through people's business premises or their homes. We've also got to look at satisfying current carrying capacity. That includes voltage drop and other minimum size requirements for conductors. So voltage drop, a really good little tip for that one is with your voltage drop calculations, once you've calculated your voltage drop, generally speaking, as long as there's no huge external fault loop impedance, if you calculate your voltage drop to be on point, we need to make sure that will make sure generally, like as a rule of thumb, that your fault loop impedance will be pretty sweet. So just keep an eye out for that one. Again, there's AS3008 is going to help you out with all that. Number C, provide reliability and electrical continuity of connection, joints and terminations. So we're going to run through how to actually correctly join cables. I'm not going to teach you guys how to suck eggs. We're just going to go through it and go through these sections one by one. We're going to have a bit of a chat about providing adequate strength of support, suspensions and fixings. So, things such as you can't hang cables off of suspended ceiling rods, etc., because they're not actually designed to take that extra weight. So we're going to start looking at running catenary cables, things like that. Making sure suspensions of, let's say, suspended sockets are done correctly. We need to look at making sure that, fixings, when we're clipping our cables, we've got enough fixings so that the cable doesn't sag unduly. There used to be a rule, it used to be 300mm. They've removed that. Every 300mm there needs to be a clip. They've actually removed that wall just basically to prevent undue sagging. We also want to ensure that any cabling that we install is actually going to will suit the intended use. So particular types of wiring systems, so for example a fire system, explosion protection, or safety services. Protection against mechanical damage. Now, mechanical doesn't necessarily mean that something's mechanical has hit it. Mechanical damage could mean anything, like some foot traffic, somebody kicks a cable, etc. That actually falls down under mechanical damage. So you'll hear a lot of people out in the field call it mechanical protection. Basically, we're adding extra protection on top of the cable, whether that's a conduit, whether that's steel, whether it's protective slabs, etc. And we're also going to make sure that we install it in accordance with the requirements of this section and the additional requirements as specified in manufacturer's instructions. Again, AS3000 will always specify back to manufacturing instructions. So, what are some of the types of wiring systems we've got? There's a lot of different ones. We've obviously got above ground, within walls, underground. There's a lot of different ways we can install cabling. Some people will only ever do it one way. They might only ever do underground work. They might do high voltage transmission stuff. They might be linesmen, so they might do a bit of underground and overhead. They're probably not going to look at AS3000 as a whole. But things we need to look out for when we're looking at table or section 3, 3.2 states the type of wiring system and method of installation used shall either comply with table 3.1 or have a degree of safety equivalent to that given in table 3.1. So as for the previous episode, I sort of recommend reading or listening to this podcast while you've got the book in front of you so you can have a bit of a look through as we go through. I'm not going to go into everything in heaps of depth here, but it's just good to be able to see what we're looking at. So for external influences, wiring systems shall be able to operate safely and shall function properly in the conditions to which they are likely to be exposed at the point of installation. So we need to start to look at relevant environmental and other influences, characteristics of the wiring systems may be subjected to, and we need to then start to think about the design and construction of the wiring system, or do we need to add any additional means of protection to provide mechanical or strength to that cabling. So there's a few influences here that they actually list off from 3.3.2.1 ambient temperature. So wiring systems, we obviously need to install a system that's not going to melt in the Aussie sun or crack when we install it in freezer rooms. So we need to select and install so as to be suitable for the highest and lowest local ambient temperatures. So where materials subject to temperature limitations are used above 60 degrees or below 0 degrees Celsius, manufacturer's instructions shall be followed. So when you buy a cable, look at the manufacturer's instructions of the cable, and you're actually going to be given some hints like, hey, is this cable actually rated to go below 0 degrees, or is it actually rated to go above 60 degrees? And I've been in some roof spaces in the Aussie heat, and I tell you what, it's definitely above 60 degrees in the middle of summer sometimes. So if you're installing cablings, especially conduit, where the conduit's going to be in direct sunlight. You just got to make sure you've got provision for an expansion. That's why you see a lot of the times that it might look nice and neat, the sun hits it, and then all of a sudden you've got this big roller coaster looking conduit. So you can actually buy expansion and contraction joins for your conduit work. Otherwise, in my opinion, having some flexible conduit to allow that expansion and contraction will do the same job. The expansion joins are like a little plastic spring almost that you glue actually it's like two couplings with a spring in between it that you glue all your it's a plastic looking spring, but it just allows that expansion and contraction. Again, it's quite expensive to buy that. It's just cheaper to put a bit of flex in there. Obviously, just making sure your flexible conduit you're using is going to be UV resistant. We're gonna have to look at current carrying capacity when we're looking at ambient temperature as well, because AS 3008 actually references like ambient temperature for Australia and New Zealand. For Australia, for cables in air, minimum design temperature is going to be 40 degrees. Obviously, if we're above that, we need to account for that in 3008. In New Zealand, so across the ditch, only 30 degrees. If we're going to bury cables direct or indirectly to the ground, so whether that's directly laid into a trench without any conduit or within a conduit system, in Australia, we say that the ambient temperature is going to be 25 degrees in that dirt as a maximum. New Zealand, 15 degrees. Next page here, so page 151 of the document is actually table 3.1. So it's just I'm not going to run through all this, but it is going to give you a list of cable types and their application in wiring systems. So it'll give you some like examples of unenclosed, it'll give you some examples in an enclosure, it'll give you support, like an example of it being supported on a catenary system, and another one supported on insulators. Again, 3008 is going to go into a lot more detail with that, so we're not going to dive into that today. We will cover off on 3008 at some stage, but not for a while. We've still got to get through AS 3000. So things that we also need to be aware of are going to be external heat sources. So, solar gain is actually a good one. So sitting out in the sun, that's an external heat source. Right underneath the tin of a domestic house, that's an external heat source. Running cabling up an old chimney that might still be used, that's an external heat source. We need to think about how we're installing our cables and what it's likely to come across. So we can either mitigate any risk there by shielding. Obviously, we can put some form of shield around the cable, whether it's we put it in within multiple layers of conduit. We can place it sufficiently away from the source of the heat. Sometimes we can't always do that. Like we need to use that cable route for particular reasons. Selecting a system with due regard for the additional temperature rise that may occur. So maybe we look at different cables. So we're not just going to use the normal TPS. Perhaps we might look at maybe running some metal insulated metal sheath cable, metal insulated mineral sheath, I should say. Sorry. We could have a look at limiting the current to be carried by the cable, so we're actually going to reduce its operating temperature. Again, that's going to be an AS 3008 question. Local reinforcement or substitution of insulating material, so whether we're going to add extra insulation material around that. Again, if we're adding insulation material, we need to start looking at derating factors for our cables. And we also need to look, or equivalent from A to E that I just mentioned. So we also need to make sure that if we're going to start wiring into equipment, that the flexible cord or the wiring between the isolator and the equipment, any of that wiring that goes through the equipment we're hooking up, is going to be suitable for any temperatures likely to be encountered or within that equipment. So we're not just going to run normal TPS cable, maybe let's say for example to a kiln, to the terminals on a kiln, because they're going to get quite hot. So we need to start looking at other options with that one. So water or high humidity, again we've touched base for this one before, but if you're going to have high humidity or the entry of water is not going to cause damage, it's not a problem. Whereas if water does condensate, perhaps let's say lighting in a cool room or specifically a freezer room actually, where you've got a really cold source, so like you might be minus 15 degrees Celsius within your light fittings. If you don't seal up those conduit entries within or use glands etc. to break that sort of vapor, like to have a vapor seal, guarantee you that will be about a week, 2 weeks, and that fitting will be full of water and your client's not going to have any lights. So we need to really be quite careful around water and humidity. We're lucky in SA, like we don't have a lot of high humidity days. Have a look at the guys and girls up in far north Queensland, Northern Territory or northern Western Australia, where they're getting those humid days day in, day out. Feel sorry for you guys sometimes. We also need to look at solid foreign bodies. So that's not people that have decided to move over and live in Australia. God bless them. It's going to be, we need to make sure we're not incorporating dust or dirt coming into our wiring system, because obviously it's going to start to really affect our heat dissipation. So we need to prevent even like stacking of dust on top of cable trays and things like that. So maybe you need to fit some cable tray lid to prevent that dust in a commercial or an industrial application. We need to sort of also have a bit of a look at corrosive or polluting substances. So you might be working in a chemical batch plant, something like that. So there'll be specific cables. You might have to use rubber cables everywhere. There's heaps of things around that corrosive or polluting sort of areas that we need to worry about. Generally, that'll be very site specific. And if you're working in something like that, generally speaking, the client will have some sort of an example of what you can and can't use. Or they'll have a engineer specify what you can and can't use. So it does make it a little bit different. We need to have, again, we're going to 3326 on page 154 is going to run through mechanical damage. So wiring systems shall be selected and installed so as to minimise the risk of mechanical damage. So again, that's, if you're mounting anything to a Stobie pole or a power authority pole, we need to have it in steel, so if a car impacts it, it's mechanically damaged, and if the mechanical damage does get compromised, we neutralise it, so that's not going to become live in the event of an accident. It could even be looking at your main earth next to your switchboard. You've got to run conduit right up to the termination point and make sure it's fixed off correctly to the building to prevent somebody kicking it and dislodging the main earth. So we either need to look at the physical strength of the mechanical characteristics of the wiring, and that's why equipotential bonds is a minimum of 4 mil. You could probably get away with your less than 0.5 ohms by using 2.5 or 1.5. There's two reasons that we don't. That's obviously for prospective fault currents. Like we don't want that smaller earth size to actually act as a fuse and burn out before any circuit protection activates. But it's also because 4 mil's got more strength than 2.5 and 1.5 mil earth. So that mechanically aids the strength is the actual physical size of that conductor. And maybe we can avoid having to put in mechanical protection altogether by the installation of the wiring system. Appendix H will actually run you through your mechanical protection classifications, and it's actually a pretty useful section of the document. All of the appendices are. I would recommend having a bit of a flick through them. We need to start to look at vibration. So in a lot of mechanical plant rooms, that's where you see those like the Wago connectors, whether it's the DIN mount ones or the push, like the ones you see a lot of Sparkies now using just for like your day-to-day terminations. Other mechanical stresses, we need to make sure that the cables aren't supporting their own weight. So we need to make sure whether we install it within a conduit that's fixed, we need to clip it to something, we support it with a catenary, or we put some cable tray up. We also want to make sure we're using the right size clips for the right size cable. with that, because we need to make sure we're not using one that's too big so the cable just flops around in there, because again, electromagnetic forces are going to be at play here, guys and girls. So if it's too big, it'll flop around by itself, especially if it's introduced with net running near other cables. But we also want to make sure it's not too tight, because we don't want to actually damage that outer sheathing of the insulation. We want to make sure we're going to use suitable connections for any joints that we do, and that's why. And also we want to make sure that there's no strain at any of the joints. For you commercial and domestic sparkies, that's why we always put cable ties onto our fan sockets, or your 413s, whatever you guys want to call them. We call them 413s, but they're just a 3-pin plug that you plug a downlight or exhaust fan into. That's why we do it. We don't want those terminations getting stressed and creating like loose joins or broken connections. So yeah, we put a cable tie on that to sort of, that's 3328 other mechanical stresses. We also have to look at flora. So flora is vegetation. So you might be putting a switchboard right next to maybe a nice wall with some ivy growing up it. Obviously the ivy is going to be pretty invasive and grow its way into there. So perhaps maybe remove the ivy, or if you can, put your switchboard elsewhere. Again, Mother Nature will take over very, very quickly. So just have to be very thoughtful of flora. Fauna, which is obviously animals, livestock, things like that. Where the presence of fauna is expected to constitute a hazard, either the wiring system shall be selected accordingly or special protective measures shall be adopted. So we've done a couple of jobs out on dairy farms, electric fencing or fencing around meter boards, equipment, etc. Because cows do tend to like using your meter boards as a scratching pole. So it's actually a funny story. Did a job out at Paris Creek, I think it was, and big Hager plinth mount board we've put in, massive run, big cables, etc. It was the middle of winter, pretty cold and miserable out there, and I was working with my back towards an electric fence, and I was just between the electric fence and the meter board, and I'd laid the meter board down, so I was just making sure once I'd finished installing it, I was wiping it off to get the little bits of mud off the back of it. And I've actually my back, it was raining, so my shirts and jumpers are all wet, and my back's come into contact with the electric fence as I'm wiping down this wet earthed meter board, and I hopped an absolute massive whack. It was pretty funny, actually. So just that's one way of protecting your stuff is through fencing when it comes to stock and fauna. But fauna can also, parrots and native wildlife just love eating the insulation off of our TPS. I'm not sure what it is. I don't think their beaks are actually conductive, so they actually eat it like right down to the copper and don't even get a whack. So we need to make sure vermin or birds, things like that, aren't getting into roof spaces where we've got unprotected cabling. 3.3.2.11 solar radiation, so direct sunlight. So we need to have a look at cabling, and if we're installing it, is it going to be exposed to direct sunlight? So we either need to select a wiring system that's going to be suitable for being installed in direct sunlight, or we need to look at shielding it from those UV, because over time, we've all seen it, cable that's been left out in the sun, it starts to go, it almost also gets burnt. I guess it is, it's getting sunburnt. And you can actually crack it. We get a lot of, in the older areas like Morph Vale down south, where they've got their old overhead supplies to their back sheds. They've just run normal TPS through the air, and the sun's just eating that away. And give it a big windstorm and then a bit of rain, we actually get one or two cools. We've got no power or power stripping, and we generally find it is actually that overhead supply. So just a bit of a tip there, if you do go out fault finding after a storm or some rain and there is an overhead shed supply, perhaps just check that out. We need to also look at things such as hazardous areas. Again, I've never actually done a great deal of hazardous area works. When I was an apprentice, I did a little bit, but yeah, that's a whole different kettle of fish. I'm not actually experienced enough in it to actually want to talk to you guys and girls about it. If you've got any questions, reach out. I'm more than happy to help find out for you. But yeah, I'm definitely no expert there. We need to start looking at thermal insulation now. in Australia, we need to look at bulk thermal insulation. So that's your like ceiling bats, wall bats, things like that. So your thermal insulation running through the wall space. So you can obviously clip it to your walls, so you're only partially surrounded by insulation. But where it passes through, like the conductor passes straight through, or the cable, passes straight through the bulk thermal insulation. These are some figures we need to use to determine in 3008 whether we're going to say it's in air touching a surface, or whether it's partially surrounded by thermal insulation or completely surrounded. So if the length is less than or equal to 150 mil of length of cable passing through the insulation, like let's say you're just going through a stud wall, like very short run, perhaps like back-to-back power point, we can actually use the in-air touching a surface rating. If it's greater than 150 mil up to 400 mil, we're just going to use the partially surrounded rating. And if it's greater than 400 mil, using the completely surrounded rating. So you'd be surprised how much that's going to derate your cable. Again, it's just so that we don't. Cable selection is basically all about making sure that we've got the voltage drop right, fault loops right, but we're not pushing the heat of that conductor up enough to damage the insulation, so we're getting insulation breakdown. Current carrying capacity, again, this is going to be more so a 3008 section. Basically, we want to make sure that we have a current carrying capacity of the conductor in accordance with 3008 that's not less than the current to be carried by the conductor. So we just obviously, again, that's that discrimination which we spoke about last week, where the cable can carry more than the designed current flowing through it. So back to that thermal insulation thing. So wiring systems in a domestic installation shall be installed on the assumption that thermal insulation in ceilings, walls and under floors, if not currently installed, will be installed in the future. So have a think of that. So if you're just laying it through and there's a chance that somebody could put ceiling bats like either side of your conductor, so then it's, fully enclosed by fully surrounded by thermal insulation, you need to install it and select that cable. So you might go from a 2.5 mil cable up to a 20, and for a 16 amp circuit protection device, just because of that lack of heat dissipation available to the cable. So it's quite an important one there. Operating temperatures of your conductors shall not exceed the limits given in table 3.2. Generally speaking, we're going to use temperatures around 75 degrees Celsius through 3008, unless we're using a more specific cable type, so whether it's rubber. There's a few examples here of using 110 degree cable, which is a crosslink polyethylene. This is table 3.2. Mineral insulated metal sheath cable, so MIMS, up to 100 for normal use for your operating temperature, but for your maximum permissible, 250 degrees Celsius. So you've got, so again, I'm not going to read through all these. Table 3.2, it gives you some examples of your normal use. Again, we're going to start to design things around that 75 degree in the domestic and commercial. And then it'll also give you some minimum ambience as well. So you can't actually use normal TPS for freezer rooms, believe it or not. Lots of people do. Conductors in parallel, current carrying capacities for circuits comprising parallel multi-core cables or groups of single-core cables may be determined from the sum of the current carrying capacity of the various cables connected in parallel, provided that the following requirements are met. So cables can't be less than 4 mil squared, so you can't use an old, for example, a lot of people use in like ducted unit changeovers. We've come across a few when we're doing our servicing. They've had an old 3-phase bit of equipment, and the client wants the cheapest option. So 3-phase air conditioning equipment is actually dearer to purchase than single phase. So they offer a single phase solution. They might only have a 2.5 mil cable, and they go, we'll just parallel up the the red and the white together, that'll be our active, and we'll put blue and black together, that's our neutral. Guess what? It's actually not compliant for two reasons. One is 343A, cable shall not be less than 4 mil. But then you also look at your earthing, it's actually going to be too small. So I just have for that prospective fault current of that cable now. So you also want to, when you do start to parallel things up, you just want to make sure that the grouping isn't going to affect the cooling of those cables. And then load current sharing between each parallel group shall be sufficient to prevent overheating of any cable or group. So we want to make sure that the conductors are of the same material and cross-sectional area with a minimum size of 4 mil. So we can't just use a 4 mil and a 16 mil and parallel them up, because obviously the 16 mil is going to have much better current carrying capacity than the 4 mil. We need to make sure that the cables follow the same route and achieve the same length. We want to make sure that they're effectively joined together at each end. So we've done a lot of rural runs where we do parallel them up. So we actually do cable joining pits. We reduce them down to a manageable cable size and then bring them into meter boards or the equipment. And then we'll put them in an active link and then off we go to the equipment. So nice and easy way of doing that. And we need to make sure we've got mutual impedance as well. So that's, again, if you see something less than 4 mil paralleled up, it's non-compliant. So coordination between conductors and protective devices, I'm not going to jump into this one too much because we covered that off when we did section 2. That's clause 253. Basically, we need to make sure, again, that our cable can carry the more than the load and also more than what the circuit protection device is. Simple as that. Conductor size. We need to have a quick look here at nominal cross-section area of conductors. So this one's really interesting. So table 3.3 is on page 160 in AS 3000 2018. Type of wiring systems, insulated conductors, socket outlets. It says here material copper at cross-sectional area. So the minimum cross-section area is 2.5 mil for a socket outlet. But there is an exception to this, exception 1 for this one. Smaller conductors may be used on sub-circuit supplying socket outlets based on their suitability in accordance with this standard and are taking account of voltage drop, current carrying capacity and reliability of connections. So if you run your cable calcs for, like, let's say somebody's extended the circuit for whatever reason in 1.5 mil, they've banged it onto a 10 amp breaker because that's, generally speaking, 1.5 protected with a 10 amp RCBA and you're good to go. There's a few other rules around that, but obviously I'm not going to jump into that greatly. We'll jump into this a bit deeper. So you can actually do it, but are you going to satisfy your voltage drop? So if somebody puts the full 10 amps through and you've got a huge long run, a good rule of thumb is minimum 2.5 for a power circuit. Other circuits like lighting, etc., we can use 1 mil. I don't know why people would use 1 mil. You've got to put it on a 6 amp breaker. It is generally solid core, which is a prick because it breaks really easily. The amount of faults I've been to looking for, we've just lost some of our lights and we're not sure why, and it's the batten holder's got 10 1 mils at it, and it's like, what? Like, who does this sort of work? Like, it's cheap, so unfortunately cheapest price wins 9 times out of 10. So table 3.3 will give you a minimum size for your different uses and also your types of your wiring system. So we've got insulated conductors, bare conductors. So your bare minimum, your bare conductor minimum size is 6 mil. Your insulated flexible conductors minimum that we're allowed to install is 0.75 mil. Aerial wiring, for copper it's 6 mil, and for aluminium it's 16 mil. So again, that's your minimum size. We can always go up to suit your voltage drop, fault loop impedance and things like that. even volt rise when you're doing solar systems, etc. Neutral conductor. So this is a good one. The minimum size of the neutral conductor shall be as follows. For single phase, 2-wire circuit, so we've got an active and a neutral. The neutral conductor or conductors of a single phase consumer's main, submain or final sub-circuit, so every sort of circuit we install as electricians, shall have a current carrying capacity that not less than the current carrying capacity of the associated active conductor or the total current to be carried where there is more than one active conductor. So we actually spoke about that in section 2 last week for your neutral conductors. Now, this is multi-phase, so that could be 2-phase or 3-phase. The current carrying capacity of the neutral conductor of a multi-phase circuit shall not be less than that determined in accordance with the following. So we're going to have a look with harmonic currents, where a consumer main, submain or final subcircuit supplies a substantial load that generates harmonic currents, e.g. fluorescent lighting, computers, soft starters, variable speed devices or other electronic devices. The third and any higher order harmonic current generated in the equipment shall be added to the maximum out of balance load to determine the current to be carried by the neutral conductor. For this purpose, the third and any higher order harmonic current in the neutral conductor shall be taken as 100% of the highest load generating harmonic currents on any phase. So, what does it mean by out of balance load? Well, in a 3-phase system, if you've got, let's say a motor is a very good example of a balanced 3-phase load, your neutral will show no current flow on it. So any out of balance neutral basically means one of the phases has more current flowing than the other two. That current then flows through the neutral conductor. So if you have a balanced 3-phase system, you put your clamp meter around the neutral, you'll have 0 amps. If you measure current on your neutral conductor in a multi-phase installation, you're not actually measuring the total neutral current of all the actives at that point in time. You're just measuring the out of balance neutral current. So that's the difference. Whereas if it's single phase, if you measure your main neutral, that's your main, that's your whole current of that whole installation. Where if it's a multi-phase site, you won't have it. Moving on. We're going to have, it does actually say a little bit here about earthing conductors. That's section 5. So section 5 is about earthing, so we'll go into greater depth about earthing in section 5. 3.6 on page 162, voltage drop. So under normal service conditions, the voltage at the terminals of any power consuming electrical equipment shall be not less than the lower limits specified in the relevant electrical equipment standard. Where the electrical equipment concerned is not covered by a standard, the voltage at the terminals shall be such as not to impair the safe function of the electrical equipment. Generally, when you buy stuff now, it's going to give you a voltage range. It'll give you a lower limit, let's say it's 220 volts, that it will function correctly. Or we look at a higher limit of maybe it'll say 250 volts. So that's the operating limit. So voltage drop is a value. So as electricians, we've got a lot of numbers rattling around in our head. One of these numbers is your voltage drop, so your maximum permissible voltage drop of the installation. Now, that's 5%. So it's not a lot, but 5% voltage drop. So that's from your point of supply. So that's generally your service fuse. So or your point of connection to the supply authority, I should say, because your service fuse could be mounted elsewhere. So from where you're connecting your consumer's mains to your point of supply, to your meter board, from your meter board to your final, like let's say you've got a submain, and then from your submain, you've then got a distribution board, then you've got a couple of final sub-circuits coming out of there. So your total voltage drop includes your consumer's mains, any sub-mains, and all the way to your final sub-circuit, you need to calculate your voltage drop. Now that has to be all fall under 5%. So we can calculate that again a few different ways. We can calculate the total of the connected load supplied through the circuit and work it out that way. We can look at the maximum demand of the circuit, so the whole circuit, or we can have a look at the current rating of the circuit protective device. So there's a few different ways. I might actually do a voltage drop, sort of a masterclass on that. Again, 3008 will run you through how to calculate your voltage drop. We use the software for that as well. Again, it's really important to use to know the manual method, so then you understand why the values you're putting into your software is actually important. Motor starting, solenoid closing, other similar applications, they're going to cause high transient currents, large inrush currents, and they're actually excluded from consideration because we expect that. Like a motor could have up anywhere between 8 to 12 times its full load current is through its startup current. So if we try to work that out, our voltage drop's going to be through the roof if we're calculating it up using those startup voltages. Appendix C is really good to give you a rough indication of voltage drop examples, but we still need to calculate it. Voltage rise, which is an amendment to this standard, is reverse voltage drop. So if we're generating power and we're pushing it back through into our system, we need to look at that. So this 3008 doesn't mention it. I think it's 47771, AS 47771 states that that's just for your solar and battery stuff. Maximum permissible voltage rise is only 2% from where you're feeding that power into your equipment back out to your connection to the network. So this one's really good. So we've got exception for your voltage drop. The final sub-circuits with the load distributed over the whole of the length of the circuit, such as socket outlets or even lighting points, half the current rating of the protective device may be used as the value of the current, and that's just because you don't have 16 amps right at the very last point of your circuit. So they've made a bit of an amendment to bring that into. You can divide. So let's say, for example, we've got a socket outlet circuit, final sub-circuit that's rated. We've got a 16 amp RCBO protecting that circuit. When we're calculating our current draw for that circuit length, instead of using the full 16 amps, we're going to just halve that 16 and that'll give us 8 amps. So we're just going to use 8 amps for that last final calculation. But we need to look at this from a point where we're having a directly connected appliance. So let's say we've got a 15 amp oven protected by a 16 amp RCBO on 2.5, because we can't. This is where we can't use that sub-circuit division method, because it's a fixed load, so it's right at the end of the circuit you've got that 15 amp load. So we need to just make sure when we're doing that, we're only ever doing it for where power's distributed across that entirety of the circuit instead of it being used right at the end of the dedicated circuit. Conductors in parallel, we've already spoken about this. That was 362. But basically the voltage drop for a circuit in which conductors are connected in parallel shall be taken as the voltage drop in one of the conductors when that conductor is carrying a current determined by dividing the value of the current of the circuit by the amount of conductors. So if you've got 2 conductors, you're going to divide this. Let's say we've got a 100 amp load. You've got 2 conductors. You've got to calculate the voltage drop for the length divided by the amount of conductors. So you're going to have 2 conductors, the load's 100 amps, so we're going to divide it by 2 because you've got 2 conductors. If you've got 4 conductors in parallel supplying, so in the active circuit, supplying that 100 amp load, we can look at using 25 amps for that calculation. So the more conductors you've got in parallel, that's how you calculate that. So there's a little bit of difference. Again, our software will design that for you. You just tell it how many conductors are in your circuit, and it'll actually give you your fault loop as your volt drop as a total, with the amount of conductors in parallel. Electrical connections. Now, I don't know, there's been to a few jobs last week even where you get to site and, I don't know, the sparky before you must have been limp-wristed. Just everything's just loose. Like, if you're working in a switchboard, even if you're only in there for 5 minutes, re-terminating it, like swapping a circuit breaker to an RCBA, just spend 5 minutes, please, running through with your screwdriver and just making sure that all those terminals are nice and tight. Because this is how we get switchboard fires, loose connections. It's either that or ingress of foreign bodies or water, potentially. But 9 times out of 10, it's loose connections from limp-wristed sparkies. So please give it another tighten. Get yourself a decent set of screwdrivers. Let's get these electrical connections sorted. So connections between conductors and other electrical equipment, we need to provide electrical continuity. So also, we need to ensure there's an appropriate level of insulation and adequate mechanical strength. So we're going to make sure we're going to use junction boxes, or we're going to use inline crimps with heat shrink. We're going to make sure that there's mechanical strength there, so there's no way that if the cables get pulled, that those conductors within the junction get pulled. We're going to make sure that it's going to be suitable for the application. So if it's an underground join, we're not just going to use a normal junction box and some blue points and throw some dirt over it and hope that the water never finds its way in. And I've seen this, a concreter's hit something, his mate who was a sparky came through to fix it. The first rain event we had, we get a call, my bore pump's not working since this other sparky fixed these undergrounds we get there, and there's just normal junction boxes just sitting in puddles of water. Absolutely atrocious. So we need to make sure we're using the correct connection method. So whether that's a resin-filled junction box after we've done some inline joins, damaged underground cable, just think about what you're doing, because you're putting your name to that repair or that join, so you want to make sure you've done it right. We need to have a quick look at the material of the conductor and its insulation. If we're joining copper to aluminium, we need to make sure we're using a bimetallic lug so we're not getting corrosive action between the two dissimilar metals. They're expensive, so if you're quoting a long rural run and you're using aluminium, don't leave out the lugs because you'll sell yourself short. We also want to have a look at the number and and shape of the wires forming the conductor and the connection. We want to make sure we're using the right size connections or the right size lugs for the right size cable. We want to make sure the number of conductors being connected together is going to be suitable for that connection device. And we also want to make sure that there's any prevention of moisture, whether that's siphoning through any cable or wiring enclosure as well. So there's a lot to think about when we're looking at doing the connection methods. Some people might only ever use Wagos. Some people might only ever use blue points. MC4 connection for your solar stuff. That's a connection. Crimp joins like cable, circuit breaker lugs, things like that. They're all methods of connection. All right. So there's so many examples. I'm not going to run through them all. You'll cover that a little bit at TAFE or wherever you choose to do your technical training. But there's multiple different ways of connecting, even CAD welding, things like that. We need to have a look, especially around aluminium conductors. There's a lot of preparation when it comes to doing aluminium connections. All sorts of stuff, from linear expansion, contact with dissimilar metals. So again, that galvanic action is going to be an issue. We need to make sure any aluminium oxides removed from the conductors, and there's actually a paste that we put on the aluminium connections. And generally, if you buy an aluminium lug, it will generally have that paste within it, so when you push it on, you crimp it on, it's already fitted there. Preparation for connection. So when we're doing this, we need to make sure that any insulation on a conductor is not going to be removed any further than is necessary to make the connection. So we don't want live copper sticking out the top of circuit breakers, sticking out the back of switches. Not only does it look sloppy, it's dangerous, and it can also prevent, it can cause a short circuit potentially as you're pushing everything back into the wall. I don't actually ever use the loop terminal on a light switch anymore. Well, I never really have. My old boss actually told me not to use it, because it's just really easy for there to be a active to neutral fault. Like, you've only got a couple of mil between your terminals. So yeah, just make sure you don't have too much copper shine. Loosening of connections, we need to be worried about this too. So connections shall be made so that no loosening is likely because of vibration. So again, going back to that motor cabinet thing, that's why we use those Wago, those spring forced connections, so the screw can't vibrate loose. We need to look at also like materials like expansion and contraction as they get warmer. So we just need to make sure that like really hot connections, like high current connections, the connection, although shouldn't be hot, but if it starts to loosen off, it'll get hotter, and that's where that expansion and contraction really starts to become an issue. And this is why we can't use solder as a form of connection if we're then going to put a screw over the top of it, because we wind the screw in onto the solder. What happens is it compresses the solder. Solder will then get warm through just the general heat within that circuit, because, let's be honest, voltage drops are a form of heat dissipation. So your cable wax then becomes like an electric element. Realistically, the solder then gets soft and the screw loosens its way around, and all of a sudden now we've got a loose connection, and it actually happens really quite quickly. So if you're going to do a solder joint, please don't put a screw over it. Crimp joints or compression joints, they need to be securely retained with a suitable crimping device. So don't just bash it with a hammer or use your multi-grips to crimp them. Get the right tool, because it's going to be designed for the purpose, and it's going to exert the correct force to ensure a decent connection, because we don't want to put too much force in it and actually snap the conductors within the crimp, but we also don't want too little force where it's just going to pull out. And there's all sorts of different ones. You can have electric crimpers, like the Milwaukee do like a battery powered electric crimper now, which is just hydraulic pump driven. You can have your hand pump hydraulic. You can just have your mechanical crimps, like your large ones. I think they do up to like 150 mil. They do some smaller versions which only do up to like 90 mil. Or you've got your small like little Kabak hand crimpers for like bootlaces and things like that. So there's so many different crimps out there, and they're all reasonably priced except for the battery ones. And any larger hydraulic stuff for the larger cables can be quite expensive. But just for the domestic stuff, cheapest chips to get the right crimper. So yeah, just fork out and don't try to use the ones on the back of your pliers, because you don't actually know how much force you're exerting when you're using that. These things are actually designed to exert the right amount of force. We need to also have a look at retention of stranded conductors. So we can't actually join together, for example, like flexible stranded to, you get that really fine, anything over 7 strands, it becomes quite a fine strand within like a extension lead or something, for example. Stranded conductors, we need to make sure we stay retained, so we need to start to either using a bootlace if it's going to go under a terminal, or if we're joining that to a TPS or something like that in an isolator, or a junction for like a blind or something, maybe, for example, blind motor. Use those Wagos, or a version of the Wagos. I like the Wago ones better than the versions of. We just need to make sure that we're retaining those stranded conductors underneath the termination device. Mechanical stress, again, it's listed, it's like the 4th time I think we've listed this. All cables and conductors shall be installed so that there is no undue mechanical stress on any connection. Again, cable tie on a fan socket. Really simple example. Meter panels, like when you pull the meter panel open on a switchboard, the connection authority, they're going to want to make sure that the cable, when you open that board up, is it's preventing any undue stress on the service fuse or your meter isolator, or back up to your main switches or your final sub circuits. So mechanical stress. 3727, oh, here we go. It actually has here about the solder connections in the rule book. I'll read it word for word. Where a soldered connection is used, the design shall take account of creep, mechanical stress, and temperature rise under fault conditions. Soft soldered connections shall not be clamped under a screw or between metal surfaces. Note, soldered connections are not permitted for aerial conductors in tension. I've never done an aerial connection under tension before. I guess that's more of a linesman thing. Flexible cords. Joints in flexible cords used as an installation wiring shall be made in accordance with the requirements of clause 3722 to 3727. So they're the ones we've just spoken about. Or by means of suitable cable couplers. Connections between a flexible cord used as equipment wiring to installation wiring shall be made in a purpose-made device containing suitable screwed or crimped terminals. And the requirements for conductor identification are detailed in 381. So we're about to get up to 381 anyway. We can't actually use flexible cable as fixed installation wiring unless it is just for like a dedicated piece of equipment. So whether it's for light, air conditioner, or it has to be actually HD rated, I believe, which, you know, in anything HD rated, like heavy duty rated, is always a bit tricky to strip, in my opinion. You can do it if you've got the right tools. Like, it's easy, it just takes time. It's not like the TPS where it's nice and easy. Aerial conductors, joints and connections. Again, it says here it shall be done without soldering, which they've already listed. They do repeat themselves a little bit in this book. Connections to aerial conductors shall be reliable and adequately protected against the effects of movement, exposure to direct sunlight, and entry of moisture, and shall be used as short as practicable. Where conductors of similar metals are joined, of dissimilar metals are joined, means shall be taken to prevent galvanic action by the use of appropriate connecting devices, or, you know, so that's, for example, using the right, like a bimetal lug, using oxidization paste, all that stuff. Here we go. We got one here, prohibited joins. Joints shall not be made in the following types of cable when in tension: parallel, webbed, or insulated twisted aerial cables. Yeah, it doesn't really affect most general sparkies. Neutral screen cables. Yeah, that's fair enough. Multi-core cables. Yeah, makes sense. Conductors of different metals. So they're prohibited joints under tension. So again, probably aerial conductor sort of use. Not sure how many non-linesmen would be doing that sort of work, but there you go, it's in our rulebook. 37210, underground cables. So connection in underground wiring shall be sealed to prevent the entry of moisture. Well, that's pretty obvious, isn't it? But there's people out there that don't do it. For my previous junction box example, solder connections for earthing conductors. Where soldering is used for the joining or connection of earthing conductors, the earthing conductor shall be retained in position by acceptable means independently of the solder. That's why you'll see a lot of older homes will have all the main earths sort of soldered. There's no real earth bar, and then they're generally taped or heat shrunk over the top as well. That's why. It's been a rule for a long time. So tunnel type connections, all screws that are in a direct contact with conductor in tunnel type terminates shall be of the type designed not to cut the conductor. So obviously any sort of tunnel type, if you do it up tight enough, it can, especially if it's just a screwing down into the tunnel, you can actually cut into the conductor. For earthing, obviously, generally we don't know we've got an earth fault until we either test it, which the clients don't test earthing because that's our job, or if somebody gets an electric shock, then we go out there and we find that the earth has been damaged. We need to make sure we can clamp, effective clamping of conductors for earthing shall be of a type, like the connector shall have like a 2-screw connection, is like the old way of earthing, or 1 screw with an outside diameter not less than 80% of the tunnel diameter, or the conductor clamped by suitable ferrules or plates in direct contact with the conductor. I remember getting wrapped around the knuckles as an apprentice once. If you're using Clipsal brought out these new screw connectors that had 80% cover. It's because the screws were quite large, and even their blue points now currently do have that 80% thing. But because that 2 screws were always supposed to be used for earthing. That's how my old tradesman that I worked with was taught. So that's what it was, and I wasn't really aware of that 80% rule. And that the new Clipsal screw connectors were 80% of that tunnel connection. So things change, products evolve to make life easier. Joints and cables, obviously junction box. We want to make sure we can't put fingers in places where we can get electrocuted. So junction boxes. We want to make sure that any sheathing or insulation and sheathing is going to be equivalent to that of what was being removed when we do a join in a cable. So like if you're going to do an inline join, put some heat shrink over it, not electrical tape, because obviously electrical tape can become unravelled. Identification. Installation wiring conductors shall be clearly identified to indicate their intended function as active, neutral, earthing, or equipotential bonding conductors. So where identification is achieved using the colour of the conductor, insulation, the colours specified in table 3.4 shall be used. So I'm not going to run through 3.4, so grab a rule book, check that out. So conductors with green, yellow, or green-yellow combination coloured insulation or sheathing shall not be used as active or neutral conductors in installation wiring. In New Zealand, use of these colours is restricted for conductors but not for sheathing. It actually used to be, instead of it being red, white, blue for your phase colouring in Australia, it was red, yellow, blue. I'm not sure how, but they thought that green, yellow for earthing, or green and yellow, or green and yellow for earthing, like on the same conductor, or just green was too close to yellow, so they've removed the yellow phasing colour years ago, and now we're going to strictly use red, white, blue. If you come across an old red, yellow, blue cable, just put a bit of white heat shrink on it, and you don't actually have to change the whole cable. We just need to make sure we identify it. Switchboard wiring is not actually regarded as insulation wiring, but indicated, like, so we can use black as active, we could use red as neutral, we could have all different sorts of colours, we could have purples in there, but we still have to use green, yellow, that can only ever be used as an earth. Internal wiring of equipment, it's a funny one. You look at a lot of Chinese manufactured equipment and it uses all sorts of different colours for different things. It's not installation wiring, so AS3000 covers off strictly on installation wiring. Equipment does have its own standards. If it has the tick of approval to be installed in Australia, it probably meets the right standards, so try not to stress too much about that. Colour ID, again, I won't bore you with that one. It's looking at conductors with black or light blue insulation used as active conductors, or conductors with other than green, yellow, black or light blue in sort of neutral conductors. So it gives a few little examples of sleeving. Sleeving of existing earthing and bonding conductors. So I guess this is a bit of an interesting one. So if you're going to sleeve an active to be a neutral or a neutral to be an active, you only have to sleeve the bit between the outer sheathing and the termination, so it might only be 100mm. Whereas if you're going to use the earth as an active or a neutral, you've actually got to sleeve the entire length. So you're going to strip it all out, sheathe it, then put it all back in to change the colour of the whole conductor, the whole length of that conductor, which I don't think I've never done it. So yeah, just don't use an earth as an active or a neutral, please. Like, it's just dumb. You're going to get somebody hurt. Moving on to active and neutral conductors. Again, they're going to be coloured, specified as per that last table we went through. We've got the issue I really see in the field is alternative and European colour cable identification colours. So in European cables, red, so the active is brown, which we all know because active is brown in our flexible cables. If you touch it, you will shit yourself. Black for a flexible cable or a European standard is light blue. Green, which is your earth, is your green yellow. For multi-phase stuff, so you might have a bit of flexible cable coming out of a bore pump or a lathe or something like that. So your brown, again, that's your red phase. Black is your white phase. Blue phase is grey. Neutral, again, is blue. Earthing is still green, yellow. Some cooktop, or like I've found a few induction cooktops, the grey and the blue are very similar in colour, so just be really careful out there. Just double check out that before you turn things on, because you don't want to accidentally fry all the electronics because you're giving them phases. All your electronic controls 400 volts instead of 230 volts, so just be careful with that. Install requirements, methods of installation. Table 3.1 again, so that's how typical wiring systems are going to see. External influences we've been over. Support and fixings, again, it seems to be a common theme, repeating ourselves with AS3000. Again, if you see something being repeated, it's normally repeated, but it's adding extra information, so it's definitely worthwhile having a look. Fix in position by suitable clips, saddles or clamps. Yeah, okay, we get that. Here we go. Where a wiring system, this is a bit different. This is what I mean about the additional information. Where a wiring system consisting of sheathed cables is installed through metallic structural members, any aperture through which the cable passes shall be bushed or shaped to minimise abrasion of the cable. Where likely to be disturbed, the cable shall be fixed in position at a point adjacent to the aperture. So aperture, hole. Just think of that as the hole. You've just created a hole through a bit of, you're wiring up a shed and you've drilled through a bit of purling channel, put a bush in there, put a bit of conduit with some form of mechanical fixing so that conduit then cannot slide. That's what they're after. New home guys and girls out there, your the ones that I've seen anyway, I've seen a few actually imported from China that don't have this, but generally speaking, your holes won't be drilled. They're all done with a press. Those presses, the cable's actually, not the cable, the metal's actually made in such a shape that there's no sharp edges. You don't have to run conduit or bushes through them. If you're adding any extra holes, yes you do. If you feel that there could become a chance that it'll just rub through abrasion, by all means just put a bit of conduit in there. You do you. This is just a minimum standard thing that we're talking about here. Suspended ceilings, I did touch about this. Didn't actually think it was a rule in the rule book. Wiring systems may be supported by the suspended ceiling system unless this is not permitted by the suspended ceiling manufacturer. I've never been to a commercial property or a commercial new build, I should say, where the ceiling guys have been super stoked that you're installing cables on their stuff. Just put catenaries up, but then you go do some maintenance and it just grinds your gears because everybody else has just either just chucked the cables on top of the ceiling tiles, which is a big no-no, or they've just cable tied it to the ceiling, the uprights, the little steel rods that the ceiling guys and girls use to support their ceiling. It's just a really bad practice. Wiring systems installed above suspended ceilings shall be fixed at suitable intervals to prevent undue sagging of cables. Catenary and cable ties, guys and girls. That's the easiest way to do that. Wiring systems likely to to be disturbed. So this is 3933, the location. So likely to be disturbed locations they deem as on the surface of a wall or on the underside of a ceiling or roof, in a space between a floor and the ground to which a person may gain entry, in parts of a ceiling space where access is greater than 600 millimeters in height. None of the old 600 mil rule. So 600 mil, what are we talking about there? Well, 600 mil is the corner, like around just before your ears in a domestic roof. You don't have to clip that. So you'll see a lot of cables installed in that space that won't have clips. It's compliant, as long as you don't have grouping issues and things like that. It could save you a lot of time running cables under 600 for clipping. If it's the middle of summer and you don't want to spend 3 hours on a roof, maybe kick a couple of roof tiles and run it all under 600. You might look at using a little bit more cable, but you're not stuck in a roof. So just use some of these rules to your advantages. So also below raised floors. So if you can crawl under or get into a place, we need to make sure we're going to protect those cables or clip them so they're not likely to be stepped on or disturbed. Support and protections. Support at suitable intervals to prevent the undue sagging of cables. This is that one where at the very start I said, there used to be a rule where it had to be supported every 300 mil. For some cables, 300 mil is more than enough for clipping. For bigger cables, maybe, but for smaller cables, if you only clip every 300 mil, that cable might sag. So maybe we need to do every 200 or 150 mil. It's completely up to you guys. As long as it's not sagging, it complies now. RCD protection shall not be used in lieu of mechanical protection for wiring systems that are likely to be disturbed. So a lot of people go, that's all right, it's on an RCD, it'll be fine. No, you're not allowed to do it. That's supplementary. RCD protection is always supplementary, so it's on top of mechanical protection. Protection? Yeah, you know what I mean. I said it twice, but mechanical protection. Protection against mechanical damage. Again, this is like the third time we've spoken about this one again. Mechanical damage shall be adequate. Wiring systems installed in positions where they may be reasonably expected to be subject to mechanical damage shall be adequately protected. For example, let's say you're crawling through a roof space and you can stand on a cable. Please put some timber over it so people can't stand and damage the cable. Have a look at Appendix H for examples of this. I'm not going to bore you with that. Wiring systems near building surfaces. So here we go. An amendment. Red star. 3942 was never in AS3000, the previous version. So wiring systems that are fixed in position by fasteners or held in position by thermal insulation or by passing through an opening in a structural member shall be protected by one of the methods outlined in clause 3944 if they are concealed within 50 mil from the surface of a wall, floor, ceiling or roof. So, guys and girls, what does this mean? If you have a stud wall frame that is 90 mil nominally in Australia, and you drill a hole in the center of it and you run a cable through that hole, you have only got 55 mil from the outer 10 mil gyprock surface to the center of that stud. Generally speaking, your cable is going to fall within that 50 mil surface zone, so we need to look at putting either it in some mechanical protection, so some steel, so that any fixings that people are putting through for hanging pictures or things like that doesn't pierce through the cable, or in this instance we can get away with RCD protection. Where does it become tricky? Sub boards mounted on internal walls. That's an interesting one. So we've actually got to protect the back of the subboard and also the sub mains running into that subboard, whether that's in a bit of metal conduit or we've got a surface, like a distance from the surface greater than 50 mil. Then we don't have to worry about it. But yeah, just a bit of steel pipe running through that to run through your double insulated submains straight into so whether it's just building wire and conduit through a steel like you would a Stobie pole connection, or or an orange circ run through that bit of steel, as long as it's double insulated and it can't chafe when on the entry to that mechanical protection. It's going to deem to satisfy that section. And also there's some pictures here from like 174. We'll give some examples of some switchboards and things like that. Also, it's going to give us 175 is going to give us some protection examples, like where we run cables through floor joists or through ceiling joists or wall frames or top plates, nogs, things like that. It's all there. So if you're not sure how you're allowed to actually run these cables, have a look at these pictures. Prohibited locations, so 3, 9, 4, 3 and 1. Wiring systems shall not be installed through any space formed between roofing or wall lining material and its immediate supporting member. So good example here, there's some pictures of it, like you've got some corrugated iron and you've got your peaks and your troughs in your corrugated iron. You're not allowed to run your cable through the peak or trough of that, because somebody on the other side, not seeing it, might put a roofing screw straight through it. We've actually had this with a gas pipe. I was fixing up some air conditioning units to the roof of a flat roof building, and I put some building strap down across the top of my Galv top hats and screwed it all off, just like the last one of the day as well. Super annoying. Chucked a large roofing screw, like an extra one, so we created a new hole on that roofing structure into the purling and hit a gas pipe. So if that was a cable, obviously it would have just damaged the cable, hopefully tripped some circuit protection, but because it was a gas pipe, had to get a gas plumber involved and remove roof sheets and all that stuff. So a bit frustrating. So just try and avoid doing all that. Wiring systems installed vertically, horizontally, and change of directions. There's actually rules around how many times and we can bend a cable and where it's got to go. Obviously, we want to make sure that our cable runs are as straight up and down as possible, or left and right if we're doing wall chasing, because then if anyone's doing a remodel, they can go, there's a power point, the cable goes straight up and down, or it goes straight across. We need to start looking at things such as bending radiuses of cables. That's specifically going to be manufacturer's instructions on that one. Right, we're going to quickly touch on 397 consumers mains. So we've got protected and unprotected consumers mains. What's the difference? Protected consumers mains is where your consumers mains connects into the supply authority's service fuses. That's protected. Unprotected is where your service fuses are within the metering facility, and you're running out to a point of connection on the street or in the unfused pit where there is no service protection devices there. So there's heaps of rules around, especially in SA now, when we can and can't use unfused or unprotected consumers mains. That boils down to basically how long the run is, the direction of the run, the building it's supplying, the length of the run as well. There's a heap of other ones. I'm not going to bore you with that. We'll go into that in another episode. Mineral insulated metal sheath cables, they look a lot like copper water pipes. I've never terminated one except for my time at TAFE. It's generally used for fire stuff or lifts, things like that, designed to run in the event of a fire. Flexible cords used as insulation wiring. So I've spoken about this. So flexible cords used as an insulation wiring shall be of the heavy duty sheath type and installed in the same manner as an insulated and sheathed cables. Exception: flexible cords need not be of the heavy duty type if used for the connection of pendant socket outlets, installed in a suitable wiring enclosure, or installed for the connection of equipment in accordance with the equipment wiring provisions of clause 4.3. Flexible cords installed as follows shall be regarded as insulation wiring and shall comply with clause 3974. Permanently connected flexible cords, including flexible cords used as pendants for socket outlets and those connected to an installation coupler. So soft wiring. Flexible cords are not open to view. Flexible cords used as pendants for lamps, luminaires, or provided with and permanently connected to an appliance shall not be regarded as installation wiring. Flexible cords installed for the connection of a single appliance or luminaire shall not be regarded as an installation wiring, provided that they do not exceed 2.5 meters in length and have a current carrying capacity of not less than the current rating or setting of the circuit protection device or the actual load of the appliance or luminaire. So let's say you've got a bit of 0.75 mil, so quite thin flexible cord, and you want to connect it to a junction in the roof to run a client supplied pendant light, for example. Do you have to derate your circuit protection to accommodate that smaller drop in conductor? No, you don't, because your lamp is going to be a fixed load, and generally there'll be a warning label in there like, please do not connect load greater than 100 watts to this pendant. That's for protecting that cable, but also to protect the pendant, the lamp, its shade itself from getting too hot. There's a thing about like low voltage track systems, also low voltage again, is not as low as you might think. Like, that's still 240 volts, that's still 230 volts, that's still low voltage. There's a section here about under carpet wiring systems. That's probably more for the commercial remodels. Basically, we need to mechanically protect that. Prevention of mutual detrimental effects between services. So this is where we're going to start running into things like different voltages levels, different electrical installations, so common enclosures, things like that. So that's a big ruling around that, like common services, trenches, etc. We need to make sure that we've got certain distances from other services. Page 184, there's a lot of examples, and it's quite good. We want to select and install cables to prevent the spread of fire, obviously. So if we're breaching through fire-rated walls, we need to make sure we're sealing that up. Penetration of fire barriers. We want to make sure we're at least 50 mil away from other penetrations. And the cross-sectional area of the opening shall be not greater than 500 mil. I.e. if circular 25 mil diameter, and the cross-sectional area of the opening may be increased up to a maximum of 2,000 millimeters squared. So for a single cable that leaves a gap of not more than 15 mil between the cable and the opening. So we need to seal up any fire-rated penetrations we do. Now, whether that's on you as the electrician to do, or whether you let the builder know you've penetrated and they get somebody in to certify it, you just want to make sure that you cover your ass and you do your best. Circulation of eddy currents. Now, this is another one, probably more so for your running large conductors through conductive base plate, gland plates, things like that. We just need to make sure we're using non-ferrous gland plates, like an aluminium would be a really good way of avoiding having all this stuff. Generally it's 300 amps and above. We need to do a slot between the individual core entries with a width of 20% of the individual core entries diameter is considered satisfactory. So let's say we do a 40 mil hole, 20% of 40 mil is 8 mil. So we just need to make sure we've got an 8 mil gap between, like slit between all your core entries, and that's just going to stop that circulation of your eddy current. So that's your induced current into metallic objects. Yeah, again, about 300 amps and up, you'll start seeing this being an issue. Enclosures of cables, so insulated unsheathed cables. Insulated unsheathed cables shall be enclosed in a wiring enclosure throughout their entire length. Exceptions, there's a few of them. Need not to be provided for insulated unsheathed cables installed as aerial conductors, enclosed in a wall cavity between an accessory and a wiring enclosure. So that's why we're allowed to have single insulated behind a power point or a light switch. We don't have to always have them in the 90Bs or those like black insulating boxes. Because that's how it is. You can't actually get your fingers in there, so single insulators are not becoming an issue. We obviously can do it within switchboards. We're allowed to have bare earthing running through roofs. or we can, if we have an extra low voltage circuit in accordance with clause 7.5. Insulated and sheathed cables, they don't need to be installed in a wiring enclosure unless we need to look at, if they're flammable, then maybe we need to. That's NZS 5000. Perhaps the cable needs to be slightly mechanically protected, so that's when we're going to start to put it in a conduit. Wiring enclosures, conduits, so steel conduit, flexible metal conduit, rigid and flexible insulating conduit, and corrugated insulating conduit. There's sort of the four. Cable trunking systems, so like your ductwork. Other wiring enclosures providing mechanical protection at least equivalent to those listed in items A and B. Water pipe is not suitable for a conduit because the poor plumber thinks, oh, this is a water pipe, I'll cut into this, I'll put a tap here, job done. You see this a lot when farmers have a crack at their own electrical. They just use what they've got in the shed. Please don't use water pipe. Please don't run cables down through stormwater pipes. I've seen that a few times, believe it or not. Change of wiring enclosures. So any change from one type of wiring enclosure to another should be made at a switchboard or by means of a suitable device that provides the complete protection of the conductor insulation and for continuity of conductive wiring enclosures. So if you're using a steel wiring enclosure and you're changing over to a plastic one between the switchboard and that, you need to make sure that the steel part is still earthed. Entry of water, again, we want to make sure that our wiring enclosures don't fill up with water because water-cooled conductors is not what we are a part of. Installation of wiring enclosures. Wiring enclosures shall be installed in accordance with safe and sound practice and provide adequate protection as required by clause 3.3 and 3.10.3.2 and 3.10.3.9. Wiring enclosures installed on roofing material shall not be installed in a manner that obstructs the natural water drain paths or promotes the accumulation of debris. I hate seeing conduits running across roofs. Sometimes it's inevitable, or unavoidable, I should say. If you do it, make sure you're not blocking water, you're not making it so debris can't pass underneath it. Perhaps installing some posts and going overhead might be a better option. Standoff brackets or blocks could be a issue there too. Support, obviously, we want to make sure that any enclosures are supported. Continuity, again, mechanical protection that is metallic needs to be electrically continual. Bending, again, we want to make sure that we're abiding by any manufacturer's specifications when we bend it. Passage for conductors, again, we want to make sure that we don't have any sharp edges on that. That's pretty well it. Again, we've got provision for expansion. We've spoken about this. We're repeating it again, which I'm not going to do. Cable trunking. Cable trunking basically covers need to be able to be opened. If need be, underground wiring systems. We might actually just chat about this all. There's category A's, category B's, category C's. Table 3.5 lists them all off. I might actually just touch base on that on another episode because it's actually a lot to go through for your underground wiring stuff. So I might call this one done. We will move on with underground wiring systems another day, I think. It might be a bit too much to chew off. Again, there's a lot of photos. I'm just flicking through it really quickly now, making sure there's nothing I can touch on quickly. We've just got minimum separation of underground services. Again, I might just touch base on that. Aerial wiring systems, we seem to have spoken about a lot. Clearances for aerial conductors, things like that. Catenary cables, etc. So yeah, there's still a fair bit to get through. It's been a long podcast episode so far, so we might just leave it. We'll kick off the next episode on the underground wiring section. I hope you guys have sort of followed through with this, with the book with me. If you've got any questions about what we've discussed so far in section 3, please reach out through any of our means, through our social media. a lot of you guys probably know me personally. Reach out, give me a ring, shoot me an email, do whatever you need to do to get in touch. But it's a pretty dry subject, AS3000. I'm trying to make it interesting and trying to read out what's most important. But yeah, it is very important to make sure you've got a big grasp on. So I thank you guys for hanging in with me. It's been another really long episode. Thanks for listening to another episode of What's Up, Mate, a Australian podcast for Australian electricians and refrigeration technicians. I'll speak to you all next week. Thanks, guys.